Okay, welcome back everyone. I'm here to provide a short overview of one of our lecture materials. A reminder that homework 2 will be assigned. It will be continuing with Chapter 1 from Koretsky. So you're going to see a continuation assessing your skills as they develop with Chapter 1 material. These lectures moving forward are going to continue with Chapter 2, so you should be reading into Chapter 2. I would suggest reading at least the first 3 or 4 sections of Chapter 2 in the coming week. Homework 1 is due on Tuesday, and please remember to follow homework expectations and make sure that you're in clear attribution of the partners that you're working with, any resources such as online notes or documents that have solutions manuals. Clear attribution is required for this class. Now, I'm going to move forward based on a general class question that keeps popping up, which is the root mean squared speed versus the mean speed of gas molecules that are vibrating around inside of a system. Okay, so what I've done is I've gone back to a website, a resource that I think you should look into, take advantage of over your college career and afterwards. It's called Hyperphysics, and it is a resource that is developed in Georgia, and the resources are pretty extensive, akin to a Wikipedia, but really tuned in to speak to students. So you're seeing this idea in this particular page for the Maxwell speed distribution. You know, what you're looking at is that kind of distribution of speeds of molecules, gas molecules, that would be associated with velocities and ultimately how many molecules are traveling at a certain velocity. And that would be encompassed within the Maxwell-Boltzmann distribution, which you're seeing right here. So inside of the Maxwell-Boltzmann distribution, you know, you're basically seeing a distribution of data that is non-normal. It is not the bell curve. There's very little that we would associate with thermodynamics that would be following a normal distribution or a Gaussian distribution. As such, here's one of our first examples. Okay, so just like our course grades, you know, we have a few people who make very high grades, a lot of people who do well or do moderately well in class, and then there's a long tail of contributors to class that may or may not show up to class and perform quite poorly, right? So non-normal distributions pretty regular inside of our lives at the university. Here we're talking about non-normal distributions for gas molecules zipping around a system. There are 3 metrics that you're looking at here: the mean, the mode, and the root mean squared speed. So if I'm looking at here, I see the most probable speed up at the peak of the system, and that is the mode. Followed by, slightly to the right, is the mean speed, the thing that you guys tend to think of as the average speed. And notice how it's slightly off to the side of the mode. A normal distribution, the mean and the mode would be the same. And then we have the root mean squared, which is further displaced to the right. I want you to look at these things because it will affect your choice of each one of these will affect the outcome of your answers in working through the homework solutions. Just knowing that the mode is the most probable speed of the molecules that you have, whereas the root mean speed is one that is often being referred to when associated with, say, temperature. From that, you should realize that each one of these 3, the mode, the mean, and the root mean squared, are what we would call summary statistics. They summarize a part of the whole distribution, but they in themselves are not the whole distribution. Just like temperature is not the actual distribution of data, it is partly a summary value that ties in with the full distribution of the speed of molecules. So feel free to explore this at Hyperphysics, and most of what we're looking at in terms of speed associated with temperature of gases zipping around is associated with the root mean squared. Here again is that same idea for the distribution. Two of the distributions that are within your textbook in Chapter 1, both of these distributions are non-normal distributions. And you see a 300 degree Kelvin system, and you see a 1000 degrees Kelvin system. Now normally, if you were looking at these two systems, the 1000 degree system should be a much, much larger curve that goes way up out of the scanning of this plot. But what we've done in this particular plot is we have normalized these two plots so that the area under plot for 300 degrees is equal to 1, and the area under the second plot is equal to 1, which now you can see that the first plot is very high but narrow, and the second plot is lower but spread out. And remember, when we think about the spreading out of the distribution of data, we're actually referring to entropy. Entropy is the dispersal of energy within the system. Okay? All right, so let's move on to our lecture materials. Chapter 2, moving forward. The idea is we've talked about energy in terms of the language, how do we deal with basic energy balances mathematically, how do we think about temperature as a mathematical concept of du ds at constant volume and constant moles. And now we're moving into the actual first law of thermodynamics. We also, in Chapter 1, of course, described the zeroth law of thermodynamics, the idea of three bodies in thermal equilibrium. But here we're moving forward into the first law of thermodynamics. Here's my detailed reading. We'd like you to read through Chapter 2.6 this coming week. Best case you can do is to read ahead of the lectures, scan the content, and write down thoughts and concepts as you're moving through it. It's going to really help your learning in the coming lectures and your ability to take notes. All right, so like I said, your strategy in reading ahead, make an outline of what's been happening. You realize that each chapter has its own kind of structured outcomes stated right at the front of the chapter. Make a short outline of those outcomes, start reading through, checking those outcomes off. All right, so into the first law. The first law concept is about energy balance, really the flow of energy from one form to another form, which is where we say energy is neither created nor destroyed for the first law. But really, better way to say that, let's say from an applied perspective or from maybe an engineering perspective, is that energy only changes forms. You go from a radiant form to a thermal form of energy to a chemical form of energy. Energy is neither created nor destroyed. It just keeps on changing forms. Okay? And we write that mathematically using a balance such that the total change in energy of the universe, this is like an integrated form of energy, delta E, of the universe, the total change in energy of the universe is zero. There's no change in energy of the universe. Inside of the universe, energy is continually changing forms, but the net energy of the universe always stays the same. And that's going to be basically a great concept to be thinking of overall. We're going to use that to really fill in the mathematical relationships of energy changing forms from the sun, which is electromagnetic radiation, to being absorbed by a leaf. That radiant energy is absorbed by a leaf and then is converted into chemical energies as sugars. Those chemical energies as sugars are then used and metabolized by a plant or by people eating those plant materials to turn that into thermal energy, which then converts into other forms of energy, and so on and so on. Energy only changes forms, and it just keeps on changing form. At any point in this lecture video, feel free to stop, pause, take a few notes, go back and read into Chapter 1 to see that you're following along between the content and the lecture materials. Right? My goal in the lecture materials is to really guide your thinking inside of the larger reading content. You really are required to do the reading. The lecture materials just help you to focus your ideas. So let's look at a system and the surroundings for an energy conversion device, ECD, again, meaning energy conversion device. Systems analysis, so I have a system on the outside, I have surroundings, I've defined a boundary around that system, which I'm drawing with a dashed line right now. Inside of the system, I will define my system according to state variables. The energy address of that system is going to be the state. Remember? We're going to have mass and energy potentially going across the boundary. Of course, energy crossing the boundary is going to be framed as either heat or work. And to get energy across the boundary, we use what is called a path function. Heat and work are both path functions. Heat as a symbol Q, work as a symbol W, and if I had W with non-mechanical work, I would have W prime with W with mechanical work, W prime with non-mechanical work. Again, standard notation, just a check here. Anything going into my system is a plus. Anything leaving my system is a minus. If I were to have an open system, I would also allow mass to cross those boundaries. Heat and work are both energy crossing the boundary. Mass is matter crossing the boundary, which then brings us back to the mental check of an open system where matter and energy can exchange across the boundaries, a closed system where only energy can exchange across the boundaries, and an isolated system where neither energy nor matter nor mass can get across that boundary. Okay. Each one of these letters here, Q and W, are actually expressed mathematically as an integrated form. And we're going to be going back and forth in the coming weeks between integrated form and differential form expressions of energy exchange. And in using differential forms of energy exchange, you're going to find both the exact ordinary differential and the partial differential formulations, and you will find the inexact ordinary differential form, the squirrely d functions, which are these differential forms of path functions. There's squirrely dq, squirrely dw, and squirrely d prime. That is my differential form for my path functions q and w. We would call these functions inexact, and we make sure that we draw the d with the sweeping back curve, whereas a sweeping forward curve would be a partial differential, which is not what we're talking about right now. Okay? So a path, the idea of a path is going to change a state from an initial state to a final state. And if I go from an initial state, state 1, to a final state, state 2, I've actually engaged in a thermodynamic process. So a path calls for a process. And if we think about state functions and states as energy addresses, we ask the question, why do states change? Well, states change because their properties change. When a property such as temperature, pressure, volume, number of moles change, then my state changes. And so we see equation 2.12a, which is showing state functions on the left side of the equation, path functions on the right side of the equation. So take a look at 2.12a in your textbook. State functions will change only due to properties. Path functions will change depending on the path that is chosen to exchange energy across the boundary. So you're going to see in that equation on the left-hand side, and we're drawing this a little larger, delta U, delta EK plus delta EP. I want you to look at what we mean by delta E. It's a generic way to talk about energy change, and we're talking about kinetic energy and potential energy. The kinetic energy of the planet spinning through space, the potential energy of the gravity well that the planet is deriving just from mass, right? Those two properties end up canceling out for most systems that we're dealing with. The existence of an external field is effectively the same for all systems that we're going to be studying. So it just leaves us with delta U. And I want you to take a note of that we've taken out kinetic and potential energy from the equation, not because they don't exist, but because they have such small contributions relative to internal energy change for most of our problems that we can ignore them for a short time. Now, again, path function means energy crossing the boundary. So you're seeing a left is a change in the system property for a state, and a process leads to different path functions. And we're going to use that again and again. I will try to keep the state function on the left side of the equation, the path functions on the right side of the equation as much as I can. Okay. Inside of this class, right, we're going to basically, as I said, neglect the idea of external fields, the idea that gravity is affecting our system, because gravity is affecting the surroundings in addition to the system there, and the net kinetic energy of the planet spinning and moving through space is affecting both the system and the surroundings, and so the net kinetic energy of the surroundings and the net kinetic energy of gravitational force are going to, in our case, going to be negligible contributions to our problem solving. Later on, we would say probably in the third part of class, we're going to bring in systems in the presence of a field. You guys know these things. They're called batteries. When I have a system in the presence of an electric field, I get new and different and innovative ways of thinking about how I can get work done or how I can get work out of the system. That will come later in class. So right now we're fixing on a integrated form that only considers internal energies change. The state function from state 1 to state 2 change is going to be represented by delta U. The capacity to do non-mechanical and mechanical work, or let's say the capacity to do work of any kind, plus the exchange of heat. So let's write that out. So I've got the internal energy change, the capacity to do work and exchange heat, is represented by Q, the ability to exchange heat, and W, the ability to do work. So I've got heat and work, and this is PV work, or pressure volume work, and then on top of that I would add non-mechanical work. The process that leads us between would be defined as going from state 1 to state 2. In differential form, which, this is probably going to be one of the few times that I start with an integrated form of an equation. Mathematically, if you want to solve problems, you generally start with the differential form of the solution and then integrate. So I'm going to integrate the exact differential of du, that's the instantaneous change in internal energy, is equal to the instantaneous changes represented for my path functions of squarely dq plus squarely dw plus squarely dw prime. Okay, that inexact relationship is challenging for a lot of people just coming into class, which is why we specifically now require you to read EME 301 math notation and the big Y. It really explains all of these notational aspects of class. All right, so then, if I know that basically the universe of energy and everything is energy and entropy, internal energy of a system basically is going to change whenever a property changes, and those are potentially happening all the time. So internal energy is going to change. We represent internal energy change again in differential form as du and in integrated form as delta U. Notice that I've got in red du with a capital U, that is the extensive form of internal energy, and below that in green I have du in lowercase u form, which is an intensive form of describing the state function of internal energy change. Capital U is just going to be joules or kilojoules. Lowercase u in this case would probably be joules per mole, or the molar internal energy. If I were to have U hat, it would again be the specific internal energy. So we've already got the equations set up. Koretsky tends to write his equations in terms of the intensive form of the system, which is really the way that we prefer to solve problems. So du is equal to squarely dq plus squarely dw. That's mechanical work for equation 2.14. The units, again, across the board are going to be joules per mole. Again, in your homework, you have to include units as you're solving your problem. I often put units in brackets just to clearly designate that we are thinking in terms of units. 2.15, equation 2.15 is a representation of a change, instantaneous change in internal energy with respect to time, which would be a rate, and that would be joules per second. So you're noting here in this equation that I have two dots above the Q and the W. The Q and the W dot is going to be squarely dQ over dt, or squarely dW over dt. It's a rate of heat change and a rate of work change. And then, of course, if I have a rate, I have joules per second, which converts into watts per mole. I've kind of taken this out of order because, again, I would like to have you conceptually starting in differential form and then integrating. So if I integrate equation 2.14, I get equation 2.13b, which is delta U. So if I integrate du, I get delta U. This is where things get a little strange, because on the right side of the equation, there are no deltas. The integral of a path function is the path function. So we get squarely dq, the integral form is just Q, no delta. The integral form of squarely dW is W, okay? Just as you're seeing there. That's going to be one of those things that you're going to need to really kind of internalize over the course of solving problems. Each one of these has been represented as an intensive form, and of course we have ways to multiply this out by the number of moles of the system and turn it into an extensive representation. Pretty easy. So how are we going to observe changes in internal energy? Basically, it's already written up for us. There are three ways to change internal energy of a system. Either I do one, I change the temperature of my system. That temperature is clearly a property. So if I change the temperature of my system, I've done well, and I will change the energy address of my system. Two, I can change the phase of my system. Change it from a solid to a gas, or as with the vapor-liquid equilibrium, I can condense a vapor back into a liquid. The temperature does not change for phase change. The energy, though, flows across the boundary, and we will either condense or evaporate liquid or vapor, right? Third, I could change the chemical structure. I could cause a chemical reaction to happen, and that will change the internal energy of systems. So there we have it. Three ways to change the internal energy of a system. Change the temperature, change the phase inside of the system, or have a chemical reaction inside of the system, right? The cool thing here is that each one of these has a relative term, a specific thermodynamic term. Change in temperature is called sensible heat. That's heat, again, is energy crossing the boundary. Sensible heat is energy crossing the boundary that causes temperature to rise or decrease in a system. Second, changes in phase. That is called latent heat. Latent heat, again, there is no temperature change. Latent heat is energy crossing the boundary to cause a phase change. That would be latent heat. And then the third, the changes in the chemical structure, we will associate with the heat of reaction, or enthalpy of reaction, as you will see later. Okay, so just kind of wrapping things up for today, I want to give you some reminders of where we've been with language and where we're heading. Okay, so essentially there's a big part of this class that is tied to language and skill, and people who get to know the language and develop their skills early are highly likely to succeed in class. So I'd like you to review the terms that you've been finding in the text and in your notes, such as what is a state versus a path, what is work and heat. Know that we've just described it as energy crossing the boundary, right? States are energy addresses, paths are associated with processes. Again, the textbook itself will have more specific definitions. I've also described this idea of constraints. You constrain the system. So we've had three system constraints so far. An open system in which matter and energy can go across the boundary, where they're basically matter and energy exchange are not constrained. A closed system where matter is constrained and will not cross the boundary, and an isolated system where neither matter nor energy will cross the boundary. We also will see, that's a system constraint. We'll see process constraints out there too. Like you've seen that word isochoric in your homework. That means iso means constant, chor, C-H-O-R, refers to volume, so that's constant volume systems. Isothermal processes, isochoric processes, isobarothermal processes. So an isobarothermal process would be baro for pressure, thermal for temperature, so a constant pressure temperature system. Same thing as you would have when you, say, bake a cake. All right. There's my open, closed, and isolated. There's my isobaric, isochoric systems that I was just talking about. Again, these are just language terms, but start digging into them and start really internalizing them. You're not looking to memorize. You're trying to get it just into the normal language that you'd be working with every day. So again, this is like learning a second language. You're going to need to practice, and you practice by talking with people and working in teams. There are going to be three other terms that I want to point out to you. One is isenthalpic. Isenthalpic is basically something where there is a constant enthalpy in the system. We'll get to that soon. There's a term called adiabatic. You've probably seen it in some of your physics classes. Adiabatic basically means there is no energy transfer across the boundary as heat. And an isopleth is a line of constant value. Isopleth is a line of constant value. So where you have those vapor dome plots of molar volume versus pressure, as you've been seeing in your first and now we'll see in your second homework, associated with the vapor-liquid equilibrium. Pressure might be a horizontal line, but there's always a isopleth of a constant temperature, usually plotted over that diagram as kind of a parametric value, and that would be isopleth being the line of constant value, and then it would be an isotherm line. Okay? All right. So with that, just look forward to discussing enthalpy in the next lecture, which will be our second state function coming up with enthalpy. You've seen it in your chemistry classes, probably in your physics classes, and now we're going to deal with it in terms of thermodynamics. All right, folks. Thank you for your time. Look forward to seeing you in class next lecture. Have a great day.